Hello everyone. So in this video, we are still at line integral topic, but we're going to explore on conservative vector field. So if you just recall again from what we learned earlier on the fundamental theorem, F bar is what we know as conservative vector field if there's a function of F such that my F bar is equivalent to my nabla of F. Alright, so and this F here, then F bar here, F is what we know as the potential function. Alright, so let's get into what we usually see in question, for example. And in question, so say whether F bar is a conservative vector field, and if it is, find F such that F bar is the gradient. Right? So this is kind of like a common question that you actually come across when it comes to subtopic or questions that require you to get conservative vector field. And so every time you see the word conservative, we'll need to recall back on this formula that we see over here. Alright, and conservative vector field also basically means that it satisfies this equation here where your F bar is equal to nabla of my F, the gradient of my F. Alright, and here, if we look at the question properly, it actually is divided into two parts. First is to prove whether it's actually conservative or not. If it is conservative, then find the F function. This F here, which is the potential function here. So first task is to prove it being conservative or not. And second part, if it is, then we need to find what's the F. Alright, so and then if we recall, how do we prove whether something is a conservative vector field? Because this just tells you that F bar is conservative such that when your potential function F actually applies to this criteria or in this box of formula that I wrote earlier. So recall that we also have seen that if curl of my F bar is 0, alright, then we can say that it is a conservative vector field. Alright, so that's another one that we can really look at. So let's first start. We want to see whether F bar is conservative vector field or not. So first step to it, our curl. Alright, if you still recall, curl is basically just your number across F, right? In this case, it will be given by I, J, K. And then, oops, sorry, I think I forgot to write down the F bar. So just allow me to write it down here. So they give that your F of xy here is x squared plus y squared I plus 2xyj. Alright. So coming back to the question. So I have x squared plus y squared here. I have 2xy during. So do you see what's wrong with this currently, whatever that I just wrote? Do you sense any issue with it? Remember, it's a nabla cross F, right? So I have I, J, K in my first row. My second row should actually be what? My second row should actually be the d of dx, d over dx, d over dy, and d over dz. Alright? And then x squared plus y squared for this one here, for the I. For the j, I have 2xy and I have 0 here. So we've covered how to perform cross product or the curl of f in the previous video, so I'm not going to go much in detail into this one. So if we just continue from here onwards, I will get a 0 minus 0 of I, right? And then minus, I will have again 0 over 0 of j, 0 minus 0 of j, plus, and for my k actually will give me d over dx of 2xy will give me a 2y. And this one, d over dy of x squared plus y squared basically gives me 2y, right? So I'm going quite quickly with this part here because I've shown it in the previous video. So you can take your time to try to validate this later, alright? But the first thing that's the most important for us to get is to prove that it's conservative vector field, and that is done through performing your curl of f equals to 0, and over here you can see that everything is in form of 0i, 0j, and 0k. Alright, and therefore your f bar is conservative. Alright, so see to that sometimes people want to be fast and they just straight away go into getting the f. So if they actually ask you to prove or to determine whether it's actually conservative or not, please make sure that we actually perform this cross product, which is the curl of f. Okay, so we're done with the first part. Here comes the second part. So for the second part, we want to find the f, isn't it? And how is f related? We have f bar equals to gradient of f. Alright, and if my f bar, I'm just going to write it down in full over here, is equal to x squared plus y squared of I plus 2xy of j. I don't have any k component here. Okay, and they want us to get the f. Alright, so the first step that we can do, alright, and is that if my f bar is applicable to this equation that we see here, which is equivalent to the gradient of f, that basically means this whole equation here is actually the gradient of my f, right? And if you recall, gradient basically is my d over dx, d over dy, and d over dz. In this case, I only have the x and y component, alright? So it's fair for me to say that my df over dx is actually equivalent to x squared plus y squared, right? So this is actually my df over dx, this is df over dy, alright? So once we have got this, right? So basically what we do is just extracting this, because this actually is the d over dx of f, alright? That's why I'm just rewriting this as such. And when I have this basically means that I can, for me to get the f, what do? You know, integration and differentiation work hand in hand together. So if this is the differentiation of it, I can actually integrate it. Alright, and if I integrate it, I'll get, say, I'll express this in terms of x, y, and z, for example. Alright, but actually over here we do not have any z component here, so just for simplicity's sake, I'm just going to put f of x and y, yeah, because it's I and j component here. So I can, after I have identified this, I can integrate it, and when I integrate it with respect to x, sorry, we have this extracted in terms of d over dx, right? So when I integrate this, what I will get is x cubed over 3. This is for the x squared. What happens when I integrate y squared? I get xy squared. Alright, and you know we always have a constant, right? And we typically, when we deal with integration without a limit, we actually leave a constant k, right? And in this case, we're not going to put constant k. In fact, I am going to put a constant and I indicate it in terms of gy. Because it doesn't matter, right? Because I am actually integrating it with respect to x. Any constant in terms of y will still give me a 0. Alright? And another way for us to look at it is that this constant here will always be referring to other variable. So for example, if I am integrating this with respect to x, then the constant here will then be expressed in terms of y. Alright? And of course, in this case, I only have my f expressed in terms of x and y. Say if I have f of x, y, z, then basically I will need to write another one for my gz. Alright? So, but otherwise, everything is just fine. But we're not quite done here. What happens when we usually have the integrated version, but we have a constant? This tells us that we still need to find my gy, right? Whatever the constant is. And the way for us to do this is then, note that earlier we only extract this portion here. Let me just use a different, so because conservative vector field applies to this criterion, and therefore f is actually the d of dx of f for the x for this one, which I extracted. That's first step. And after we have identified the df of dx, we integrate it to get the f of xy. And since we integrate it with respect to x, we have a constant. Do include the constant, and we express it in terms of y here. Now comes the part where we are kind of semi-done, but at the same time, we still need to get what is the gy. So what else or what other resources can we use? For us to get the gy, alright, then basically, I get this as my f of xy. So we're playing around with the differentiation and the integration a little bit, yeah? So we have got this. Earlier we integrated with respect to x. So now what happens is that based on this earlier, to find my gy, what we're going to do is that we're going to differentiate it. Alright? And now I'm differentiating this again, but with respect to dy. So no worry about it. I mean, like, yeah. So I can write this as df over dy. I'm differentiating it with respect to y. And based on this expression that we got earlier, if I differentiate this in terms of y, it gives us 0. This one, we get 2xy. And this, basically, is a g prime y. Right? I'm going to put this as equation 1. So you see where it is going, right? And then, similarly, what other resources can we get? No worry if it takes a little bit of time to just look at how things work around here. So that's the beauty of this video. You can always pause and just rewind and look back at whichever part that you need more understanding on. So once we have got this f of xy, we need to find the gy, and therefore I differentiate this in terms of y, and I get this, right? And why, just in case you're wondering, why do I differentiate this with respect to dy? So do you notice that earlier, based on whatever information that they already gave us, which is this f of xy is equal to this expression here, and thus far, whatever information that we use is based on this first term here in terms of the x, right? So basically, now, if this is actually my df of dx, right? This is actually my df of dy, right? Doesn't it make sense? So, if I just rewrite this, this is actually my df over dy. So df over dy is actually 2xy. I'm going to put this as the second equation. So do you see what's happening here? So basically, based on the first information, we got the f, and then after that we will try to get, and then we differentiate it with the other, with respect to the other variable, because earlier we used the x component, right? So now I get the d over dy of fxy. That gives us this part here, but at the same time, I can use the information from the question, the one in purple here, which is 2xy, and it actually indicates the same thing, which is df over dy equals to 2xy. And what happens, let me just scroll this a little bit up here. What happens is that once I have got this, basically we can compare 1 and 2 because they're literally the same thing. And when I compare these two components and all that, you will notice that my g prime of y is actually just 0, right? And if my g prime of y is 0, recall that from the beginning itself we want to find what the gy is. If I integrate gy, then it's just going to give me any constant k. Alright? So in this case, I'm just going to scroll this up a little bit. Therefore, my f function is given by x cubed over 3 plus xy squared plus k. Alright, so this is the potential function of my conservative vector field. So recall that, just some important note so that you do know what the question requires you to get next time. Alright, so just so happen that this is, just in case you're wondering, like, if I just put k in replacement of my gy earlier, it will still lead to the same answer. Just so happen that this question gives you the same answer of just a constant k. At some other questions and all that, sometimes it could be of some other number and all that. Alright, so please look at it again. I mean, like, and try to analyze how things are. Alright, so the important points that we learned in this video here basically is to perform your curl of f. And if you get it equal to 0, then you manage to prove that it's a conservative vector field. And if it is a conservative vector field, we do know that your f bar is applicable to this nabla of f. And in this case, what we have to do is literally just make use of this equation here and try to get my function of f by differentiating and integrating. There are, of course, a few techniques of where we want to differentiate it and how we want to integrate it and all that, which one and all. Just in case you're wondering, because earlier, I'm just going to scroll this back up a little bit. Because earlier you wonder, like, okay, we first started with df over dx of this one. What if I want to try it out with my df over dy first? It's literally up to you. Alright, for mathematics, there's no one-way solution. It's as long as you can also even start out with the one in purple first, and then eventually we're still going to arrive at the same solution. Alright, so good luck in trying and happy studying.